Thank you very much. Good morning. Thank you for coming along. It's a good turnout after last night. Okay, so I'm going to talk about relaxometry of the heart. So, yeah, some disclaimer there. Relaxometry is an old-fashioned term, actually, to describe the study, relaxation behavior of spin systems in NMR. And often T1 and T2 were measured as a function of magnetic field strength, something we don't do anymore, to probe the water's interaction with its environment. And in the 80s and 90s, this was a hugely big field, and people were trying to understand the water and what was going on. But now we take it for granted, and especially in cardiac MR, we've kind of forgotten it. And so it's kind of interesting that we're rediscovering it again. Obviously, in the early days, this didn't use imaging readouts. And I'd steer you towards the Encyclopedia of NMR, which is a great book, ridiculously expensive, but if your university has it online, it's excellent. And there's a great paper by Seymour Koenig in that. So just as a reminder, I didn't know how many clinicians would be present, so sorry if this is also obvious. So T1's the spin lattice decay constant for recovery of the Z component of the nuclear magnetization. And it's magnetic, it's scalar independent, but obviously it depends on field strength to some small degree. Whereas T2 is a spin-spin relaxation time and is a decay constant of the component, the M, the magnetization once you've excited it. And it's pretty much field independent, a little bit shorter at 3 Tesla than 1.5. And then T2 star is a relaxation of the gradient echo sequence. So it's always shorter than T2. And it's basically linear in field strength. Yeah. Just another one, really. So in this case, this is a demonstration of T1. So in this case, we've got an inversion pulse, and this is the MZ magnetization as it recovers. And so the exponential recovery rate of this is defined by this T1. Whereas in the T2 case, we've excited the signal, and this is the magnetization in the transverse plane, so effectively the signal we can see, and this is decaying, and this decay constant is exponential T2. So a bit more background, basic stuff, but we tend to forget it. So most tissues contain an incredible amount of water, about 80% of water in nearly all tissues, and consequently proton density isn't actually that useful. There are exceptions to this, white matter, things like that, lung. But typically, proton density is not very useful at all. But all the tissue water is essentially liquid that we see, and we're observing this in the motional narrowing regime. Diffusion in tissue is actually very high, so it's a third to a half of that in pure water. And at current field strengths, the T1's typically 10 times the T2. And then we've got compartments. So we've got intracellular and extracellular compartments. We've got other compartments. But the cell boundaries are actually highly water permeable. And at the timescales of T1, all those components are actually visited equally. So that's quite an interesting characteristic. And then just a reminder, because sometimes we have to talk in terms of R1s. So R1's 1 over T1. And R's useful as a relaxivity. It's the more natural way of describing some of this relaxation, whereas T1 and T2 are more convenient experimentally. So we might use them interchangeably. So here we go. Histology slice from a pig. So the purple stuff, the pink stuff is myocytes, and the white stuff is in extracellular space. So the intracellular T1s and T2s are quite shorter, owing to the water interacting with the immobile proteins, the high concentration of immobile proteins. Whereas the white stuff here, pointed to by the arrows, is extracellular water, and that has longer T1 and longer T2, as there's fewer relaxation centers. So in the infarcted case, the extracellular space is increasing, and so you're going to get more of this stuff. So on the timescale of T1, so of the order of 1 second, the water actually sees all spaces. So this is a blue line demonstrating the diffusion of water. And as you can see, it moves between all these different spaces. And so it samples them equally. And so we can apply this motional narrowing case. And so the R1 of this water will be the sum of the R1 in each environment multiplied by the amount of time it spends in each environment. So this kind of ends up being a weighted sum. And we know this is actually a pretty good model because when you look at the exponential recovery curves of T1, they do demonstrate a single exponential behavior pretty close. T2 is not quite so simple as that. Other things also affect T1. So fat, flow, contrast agents, iron, and fat that people talk about being fat that isn't fat. Now to mapping. You're probably familiar with mapping, but this is it's a great way of displaying information, isn't it, mapping? So here we go. This is a map of the world. with the hellish journey you have to come to here, which is a lovely place. Another map, so in this case, you can show lots of different things on maps. So this is politically coloured. This is elevation, for example, so the different heights of different places, the height of the seabed and stuff like that. So you can show lots of different things on maps. And you can show them politically as well. So in this case, this is heart disease rates in the US and plotted against distance from the nearest McDonald's, which is a kind of mashup. Anyway, so the simple goal is we want to generate a map in the heart where we've got these MR tissue relaxation parameters at each pixel. And the question is, like, you know, it's in 2017. We've been doing relaxometry for a long time. We're doing cardiac imaging for a long time. Why is it only now? And it turns out it's actually quite difficult. But T1 mapping is now available as product, so you can buy it from the manufacturers on Siemens as MyMaps, Philips as Cardiac Quant, and GE have a smart T1 product, which is going to be released quite shortly, I'm told. T2 Star, on the other hand, is actually quite a mature technology using gradient echoes, and T2 mapping is not really yet mainstream. But all these three things are available quite widely in the research community. So this talk's going to be about T1 mapping, touching on ECV, extracellular volume. I'll briefly mention T2 Star mapping, and then I'll talk a little bit about T2 mapping. But there are other mechanisms of contrast and relaxation, which I'm not going to talk about today. So sorry if you're disappointed and you came to hear about those. So just a reminder, really, the gold standard for T1 mapping is T1 imaging, if you like, is an inversion recovery sequence, a spin echo-based, an inversion recovery method, where we're inverting with 180 degrees and we wait a period of time and then sample that magnetization. And then you wait a long time for it all to recover, maybe 5, 6 TRs, and then repeat again. And so, you know, why don't we just use that in the heart? So it's quite simple, really. So if you've got a TR of 10 seconds, and you've got maybe 10 different TIs, so different TIs you want to measure to sample this curve, and then you have 128 phasing codes, then it gives you a 4-hour acquisition, which is a long breath hold even by graduate student standards. So consequently, it's not easy. So fortunately, Daniel Messerogli, when he was at Leeds, did some work on this and invented this modified look locker inversion recovery sequence, this MOLLY sequence, which we always just call it MOLLY. So. And what this does, the look locker part is effectively saying what we're doing is we're collecting data, multiple data points on this recovery curve. So we're inverting the magnetization, then we're sampling on this recovery curve. So the look locker is talking about the fact that we're sampling multiple times. And then it's modified by the fact that we do several different inversions and then interleave them. So just to demonstrate that here, after the first inversion, we collect 3 images. So these are all cardiac gated at the same phase of the cardiac cycle. And you can see here, so if we look at this single pixel, we can see we get the signal from the purple points from this first inversion. From the second inversion, we're getting the red points. And in the third inversion, we're getting these other points. So what happens is the reason you do this is you need to get data points at the same cardiac phase, but you want data points more frequently than the RR interval. So this allows you to fill in the gaps. So that method works quite well. What you get out of that, you get T1 star. So in actual fact, T1 star isn't equal to T1. And because the reason is in this look locker mode, the magnetization doesn't recover fully to M0. So you can see here. So what we can do is we can correct that. There's a well-known correction, which is actually wrong, but everyone uses it, and so we blindly go ahead with it and occasionally put in the odd adjective in our method statement, so because to demonstrate we're clever, but not clever enough to fix it. So therefore, you can get a T1 map out of this, and this is the sort of thing we're doing all the time. So you can see, you know, your blood pool here is a T1 of, you know, order of 1600 milliseconds. This is color-coded to the color code we use. So green is used for the healthy myocardium, and you can see all the tissues as well. It works very well. So in Oxford, we were a little bit worried about this. We liked it, we used it, but our radiographers always got cross with us because it just took too long. So 20 seconds is fine in a healthy population. You know, everyone can hold their breath for 20 seconds. It turns out patients can't hold their breath for 20 seconds. So we developed this SMOLLY sequence, shortened MOLLY, which just requires 9 heartbeats, which I'll talk about in a second. Here we go. So this is the MOLLY sequence. This is the SMOLLY sequence. And so what it does is it does a single inversion and then collects 5 images. then it has a pause and collects one more image, then a second inversion with another image, and a third inversion and another image. So it's very simple. And then what it uses a nonlinear reconstruction algorithm, which is kind of the clever bit, if you like, that sometimes uses these data and sometimes doesn't, depending on whether the T1's long or short. So when the T1's long, you don't need these data points. And in actual fact, they're not very good because the magnetization hasn't recovered properly. Whereas when the T1's short, the magnetization does recover properly, and these are useful points and necessary. So that's the magic of Schmoly, if you like. So just in terms of some quick results on Schmoly versus Moly, as you can see, this is the original Moly method. So using that 3-3-5 prototype, which doesn't turn out to be very good. So there are other better ways of doing it. But in that case, comparing with that, the Schmoly method, looking at different heart rates, you can see that the Schmoly method is kind of heart rate independent, which is nice, and which is validated in simulation and in phantoms. So heart rate independence is kind of a nice feature and quite useful for T1 mapping. There have been variants of the Moly method that have come out now, which change the delays and overcome that problem. So generally, this isn't necessarily a problem, but the heart rate independence of Schmoly is a kind of useful thing. And just a simple example, so this is a patient with anterior myocardial infarction. Green is healthy. This color is not so healthy, so we've got some disease here. You should also note that basically the images agree. The Schmoly method is slightly noisier in actual fact because you've got fewer data points, so it's not a great surprise, just less signal averaging. A point to note, this is at 3 Tesla, and you've got this small SSFP artifact, and you do get some artifacts from all these methods, so just the normal problems. Oh, sorry, late gadolinium enhancement showing in the region, so it's not really the most difficult radiological problem, that one, is it? So in terms of T1 Moly-based methods, Moly has become the standard approach. So effectively on the 3 vendors, they're providing a Moly-based sequence that at least you can implement it as a Moly-made. It's really highly reproducible, which is its great strength. It's robust, and it's proven to be diagnostically useful. It's got some disadvantages in that the T1 isn't the same as the gold standard, so it's not really the T1. And the measured T1 is influenced by T2. It's also influenced by the presence of fat, and it's influenced by the effects of magnetization transfer. So really, whenever I talk about it, I prefer to call it Moly T1 rather than T1 because it's not actually T1, but that falls on deaf ears with my clinical colleagues generally. Other methods are available, and sorry, I haven't really got time to talk about them, but the Sasha method, Sapphire, are all very good methods, and they have strengths and weaknesses, but none of them are sufficiently much better than the Moly method, and the Moly method's got quite a lot of inertia now, so it's well adopted. So it's likely that they'll struggle to have the same level of adoption, but who knows? Here's some data we did across 3 centres. So this is all 1.5T, and as you can see, the range of this. So this is the maximum here is of 980, and the minimum is about 930. And this is different with age. So women, premenopausal women, have longer T1s, but the numbers we get are very tight. So there's some quite interesting tight numbers you can get out of these sort of data. And it works across centres. It's the same everywhere. It just kind of works. I did some work in the early days in reversible edema. So this was based on wall motion as the metric. And this is an ROC curve showing the Moly method as compared to the standard T2 method. So stir based on remote myocardium, stir reference to muscle. And as you can see, this is superior. So T1's a good method. Another area it's useful for is in amyloidosis. So in amyloidosis, you're getting massive disruption of the cellular matrix, and so you get much larger extracellular space. And as you can see here, a green would be a healthy myocardium. In this case, it's got this patchy yellow-orange color, which is indicating you've got global changes. Now, global changes aren't very easily detected with lots of techniques because often you're doing a comparison. So, for example, with late GAD, it would be quite difficult because you have to choose an inversion time, which would correspond to black for normal tissue. As there's no normal tissue, it would be very difficult. So this is kind of a useful technique in that way, and it's kind of a very definitive statement. We didn't really set out to image fat, but interestingly enough, it images fat quite well. So in this case, we've got it's an ischemic cardiomyopathy, and you've got some fatty infiltration here. and that detects it quite well, and the blue colour that we use in our colour map is definitive for that. So you can see how it's working really rather well. So it's very simple. So it just adds information very cheaply. So I should talk briefly about extracellular volume. So James Moon, London Heart Hospital at the time, did a lot of work on extracellular volume, pioneering that method. And so what he uses is effectively, it allows you to quantify the volume of space outside the cells, the extracellular volume, quantitatively. And what you do is you effectively collect an image T1 map, pre-contrast. Then you inject contrast, gadolinium-based contrast, and wait about 20 minutes. And it's freely diffusible, so within that interval, it's uniformly distributed through a whole plasma. And then you measure the blood and myocardial T1 again. And then what you can do is you can work out based on the R1s, how much the R1s changes due to this gadolinium and the concentration in the plasma, and therefore determine the ECV map. And that's benefited hugely from fast T1 mapping. So originally they used slow methods for measuring T1, but now with fast T1 mapping you can do the pre-measurement in one breath hold and the post-measurement in the second breath hold, and you can get good numbers. So there's a good summary paper on this. So this is sort of driving it towards clinical adoption by having a consensus paper, which is well worth a read. So in terms of ECV, it's quite interesting. So we've already said that the native T1 is a weighted sum of the intracellular and extracellular R1s. And so really, in many ways, you've got an obvious linear correlation between the native T1 and the extracellular volume. So you increase the extracellular volume, the water spends more time in that long T1 environment, therefore the native T1 increases. And this behaves very well. Obviously, there's some interesting stuff in terms of acute MI and chronic MI. So this may be related to cell rupture or cell swelling. I'm not quite sure. And then you've got some outliers. So fat's different. It's just a different molecule, so it's obviously not going to play the game. And then Fabry's disease and iron are different. So I'll just talk about those briefly. So here's another graph from Dan Sado from James Moon's group showing the T1 you get at 1.5 Tesla in different diseases. So in amyloid, the T1 gets very long. In all these hypertrophic conditions, you get an increase in T1 because you're getting more extracellular space. But in Fabry's, it actually decreases. So Anderson-Fabry's disease is a disease where you accumulate glycosphingolipid, which is interesting. And your clinicians say, oh, well, it's got short because it's got lipid in it. But it's not like that. So if you do MR spectroscopy on this, you don't see any CH2 groups. It's not lipid at all. It's much more like white matter, which has the same characteristics. It has this shortened T1 because effectively the water's interacting with the glycosphingolipid proteins. So that's one to look out for and explain to them politely. Cardiac iron determines cardiac iron's the other one. So this is from John Moon's great paper where he looks at T2 star, T2 and T1 after loading up gerbils with iron. And as you can see, so here we've got the rate, so 1 over T2, so the T2 decreases with increasing iron. Similarly, the T1 decreases with the increasing iron. So this is a direct effect. It's not really surprising given how we know the magnetic properties of iron. And so that's something, obviously. So if you have elevated iron, you're going to decrease the T1s as well. And that may be a method to determine the concentration of the iron as well. So that's been shown. So here's sort of a summary. There's an extra data point here. So blood volume also plays a role. So if you increase the blood volume, if you expand your vascular space through stress, for example, you can see changes in the T1. So this is recent work from Alex Liu in Oxford, showing you can get these 60 millisecond changes with stress. And the wonderful thing about that is you can stress patients and you actually see smaller increases demonstrating their reduced vascular reactivity. So that's quite exciting. But in terms of the summary, so ECV has a big effect on the T1. Hematocrit has something of an effect, a bigger effect on ECV actually. Iron decreases T1. Alien proteins, they're not really alien, they're glycosphingolipids, but they're ones that shouldn't be there. And fat is obviously got a very short T1, although Peter Kelman's got a nice paper showing that when you get mixtures of fat and water, you get complex changes in the measured T1. And then cell swelling will have some influences too. So now to T2 star mapping. I've already kind of touched on it with the iron, if you like. It's a mature technology based on multiple echo gradient gradient echoes. So effectively, you just collect a gradient, these data and look at the signal decay. You have to worry about some things, but it's well referred to in the literature. You need a very short first echo time. You might have to worry about fat in some organs, not so much in the heart. And it works very well. You can run with a short TR. You can run this on any scanner. You've been able to run it for a long time. And then the fitting can be quite challenging, simply because you have to worry about the noise floor. But it works very well. And the correlation between iron and this R2 star is lovely and well referred to in the literature. You have to remember what field strength you're at, but generally it's a straightforward technique. So that's sort of standard stuff. Now to T2 mapping. Now T2 mapping is really interesting in that it's come along quite late and it's quite difficult in the heart. So the method that's been pushed forwards successfully is a T2 prepared method. So I'm going to talk about that in a second. But the obvious way of doing T2 map is with a CPMG, a multiple spin echo sequence. So that's the standard way of measuring T2 and the gold standard, if you like. But in actual fact, it's very difficult because of the times required. So that's what's held T2 mapping back. So just to talk about T2 prep, these are data from Giry at Ohio State, or he was at Ohio State now with Siemens. Effectively, what we've got, we're going to do a single shot acquisition, and we're going to prepare the magnetization differently. So we're going to give different T2 weighting. And then we're going to fit it, and the signal is invisible here, but effectively fit it to the obvious signal curve, and probably some noise terms and stuff. And then you can get a map of T2. So this is obviously the best one he ever did, but that's good. So just to summarize the sequence, effectively you wait for the magnetization to get to equilibrium, so leave the patient to warm to the temperature of the spins. And then we've got a cardiac gated T2 prep interval, no T2 prep in this case, sorry, and a single shot SSFP. Wait again for the magnetization to get to a steady state. And then we run with a T2 prep of 24 milliseconds and collect another single shot image. Wait to get to steady state and do the same again. So the downside of this technique is obviously you spend an awful lot of time waiting for it to get to steady state so the T1 to recover, which is a bit unfortunate. But all in all, that's sort of where you get these data. So he does a 3-point T2 fit. And he's validated this in a few cases. So there's 24 patients in this study looking at acute myocardial infarction. And as you can see, the gold standard is a TSE stir-based method. So effectively, heavily T2 weighted, looking for bright signal. And then you normalize that. You compare it to other bits of signal. So either to skeletal muscle or healthy myocardium. But he sees massive improvements, so 67% up to 96%. And it's a very successful method. The nice thing about this is you can quantify your threshold. So that's one of the nice things about all this quantitative imaging. You can say, anything above 100 is disease, or do whatever you like with it. And here's another few cases, just demonstrating the consistency and the pattern of enhancement you get with these T2 maps, consistent with STIR in this case, although he's got examples where STIR doesn't show it, but always consistent with the late GAD. So indicating, you've got lots of extracellular space going on. So that works very well. The downside of the T2 maps, in a way, in this case, is the image quality isn't that good, and they're quite difficult. So that's sort of a challenge. So, sorry, one more. So yeah, he sees group statistics demonstrating clear signal changes in infarction. And as you'll note, the changes in T2 are actually larger than you get in T1, but the ability to measure a type T1 is quite high. So it sort of all comes out in the wash. But the changes in R2 are quite large. So, but the limited image quality of the T2 prep method sort of steers us towards other approaches. And we all know fast spin echo gives you very nice images. So fast spin echo is limited in the time. So there's a couple of approaches to deal with that. So some of these very rapid, clever approaches of compressed sensing and combining data through time, because what we're going to have to do is you have to collect all those phasing codes, but you also have to collect a series of echo times. And the downside of a spin echo method is that you need to wait a reasonable time for recovery. So the cost of that is you're struggling to fit that into a single heartbeat. So this data uses this accelerated methods to do that. The other approach is to do it a different MR approach. So in this case, they've used Gray's, which is effectively a fast spin echo method, but collecting more than one line after each 180. So like a sort of an EPI type readout in there. And as you can see, this shows pretty good data too. So I think T2's got real potential with these evolving fast spin echo-based methods, which are coming through at the moment. So just to summarize, really, relaxometry is very relevant to CMR, and it's already demonstrated some really wonderful clinical benefits. T2 star is widely used, and it's really for ion overload, and it can be used for modeling, following patients up. And really, it's kind of a mature technology. It's not really clear where that could go. T2 is an alternative to STIR, and is shown to be very useful in this potential. And then T1 is being adopted in various clinical guidelines and is available on clinical scans with processing. So that's kind of perhaps the most advanced of those, of the T1 and T2. And these quantitative methods, thresholds, allow people to make more quantitative diagnosis, and they kind of de-skills it, which everyone likes. But obviously further work's needed. So it'd be nice to get higher quality maps, and it'd be nice to understand this better. So what are the differences between, what does T2 give you that T1 doesn't? So maybe there's some differential information in there. And as it's flashing red, I will stop. Thank you very much.